apart from extending the traditional astronomy to the high energies, another thing is how do we know that a source will emit only in certain bands, like only in optical or something like that. So we actually know now that there are sources which emit in very high energy bands too. So these are another reason to do multivalent astronomy. Another very important thing, which actually was one of the, let us say, triggers for studies, these studies, is what we call cosmic ray origin. And I'll explain to you what cosmic rays are. There's a very high energy charged particles, and we want to know where they come from. And unfortunately, we do not know even after almost 100 years, because they are charged particles, they don't point back to source. So, but they make photons or gammas which would point back to the source. So these are some of the reasons why we want to go to higher energies do higher energy astronomies. Now, for example, this is just to tell you how things are different. Now, this picture shows you our own galaxy in three different wave bands. Optical is the left, the radio is in the middle, and X-rays at the extreme right. You see how different things are. For example, the shapes are different and things like that. Now, let me show you another very interesting source. This is a what's we call Crab Nebula, which is you will hear more about it in my lecture today. This is probably one of the most important source in high energy astrophysics. And at this moment, I'll just say that much. But you can see how four different wavebands show you the four different aspects of this, this Crab nebula. Okay, you can see the X-ray, for example, which is it looks like something spinning, and you see the optical, much more familiar to probably some of you. So these are some reasons to why multivalent studies are got to be conducted. And this is only the qualitative aspect I'm telling you, but quantitatively, of course, more things are there. Now, this is another thing which I won't go into, but you could just see it later. This is about pulsars. Now, I talked to you about why we got to do it. Now, what are the type of sources we have? When we say sources or objects, these are words which we keep using. And so let us look at some of these things, as it's possible that you are already familiar with some of them, but for continuity's sake, we will do this because these are very important for high energy astrophysics. Now, as we already said, astrophysics at high energies deals with X-rays, gamma rays, cosmic rays, and high energy neutrinos. And as you might have gathered, high energy, if you want to produce, there got to be very high temperatures. But if you do not have high temperatures, you got relativistic particles. But we'll see how we can do it. By relativistic, what we mean is very, very high energy particles. Okay. And another thing is, this usually requires compact objects such as white dwarfs. We'll see what they are. Probably you know this, but we'll come to that. Neutron stars and black holes. That means essentially very high gravitation in these objects. We'll see how these will make high energy particles. Now, which the type of objects which we are going to be dealing with today, and as I said, you may be familiar with some of these supernovae and the remnants. Remnant means what's left behind, and then what happened in pulsars, and then other things like quasars. And another word for today, which quasars were more common this a few decades ago, but today we call everything active galactic nuclei. And then galactic center itself, our own good old galaxy. That center is very interesting. And there are phenomena called gamma ray bursts. And there's also new physics. And some of it we'll talk about, not necessarily all of them. And supernova, these are all very cursory type of look at some of these things, deeper things. So you'll hopefully you get triggered by this study, the deeper aspects. Now, as you know very well, stars are powered by nuclear fusion. Okay, and they convert hydrogen to helium, etc. And then finally you get the new elements. Now there is just a picture of kind of a cartoon picture on the left-hand side, top off. Now they also expand as they grow old, and when it runs out of hydrogen or then helium, finally it becomes less bright. This is what we call a red giant, a red supergiant. Now you may be familiar with that. In Orion Nebula we have this very famous Betelgeuse. Exact pronunciation I may be slightly wrong. And that is one of the red giants, which is very huge object. And now what happens is a supernova occurs at the end of a massive star's lifetime. And what exactly is the process? You'll see they will be very bright initially, and for quite a few weeks or months they will stay there in the skies. And also another interesting thing, which is which we should know, is when actually the star goes into the supernova phase, it also makes very high mass objects which are otherwise not available anywhere else, like gold, etc. And well, that's why the famous statement, we are made of stardust. Okay, here is a very simple this thing of what the supernova is. For example, you please look at the right hand part, and there's an arrow showing, and there is nothing there in the sky, anything spectacular at least. But then some days later, I'll tell you when exactly it happened, we have a very bright object. This is a very famous supernova called supernova 87A, which is what, about 23 years ago now. And it happened in the part of southern sky in just our neighbor galaxy. And it has become a very interesting thing because supernova theories were floating around for a long time. Now this supernova proved that almost all those theories are correct. Now this is just a cartoon again in the left part, and now it goes into the supernova phase. And this happened actually February 23rd of 1987. Now, as I already told you, Crab Nebula we are going to talk about. I always come back to this because it's the classic case of a supernova. And interestingly, just I'll take a few minutes to tell you the story of that. You see, Chinese were very good at looking at the sky, and they kept a track of whatever comes in the sky. And they had recorded in 1054, July 4th, that a very bright object came on the sky, and they always called them guest stars. And that's in Taurus constellation, as you probably astronomers may know where Taurus, the one Taurus constellation is. But okay, let's forget about all that. We don't know. And then the Europeans started their own work, and they found a very interesting object with their first telescopes, and they called it Crab. And much later, almost 200 years later, some of the people like Hubble, etc., they made connection between these two things. Okay, they said the star which was seen by Chinese at that time, and today what we call Crab, is essentially the same. So Crab is a very interesting history. I'm just giving you a very basic aspect of that. And this is this is the wonderful optical pro, I think, from the Hubble this thing. And as I kept saying, probably it's the most important source. And we'll keep hearing again, as I said, more and more of Crab. All right, now we told you what happens at the end point. I know what happens, for example. Now you have a bright object there, and sorry, you have a supernova. But then what really happens to a star, the star, original star? And then what happens is it becomes very compact, and now we have what's called a white dwarf, a neutron star, and a black hole, depending on how massive the star was initially to start with. Now the left part of there's a small cartoon type of thing at the what is it? The bottom left, comparing Earth with white dwarf and the neutron star. Now you can see white dwarf and Earth are essentially the same volume, and that is one solar mass will go into it. Whereas neutron star, you can see very clearly that it's just a dot. And what the neutron star, the basic things I'll just tell you in a few seconds, that these are just very small, 15 to 20 kilometers in diameter, and a solar mass and a heavy magnetic gravitational fields.